So this first page is kind of dumb, and I'll show you why. So we know electronegativity increases across, it decreases going down. We're reviewing electronegativity because if you remember the difference between an ionic and a covalent bond, do you remember the chart where there's like that continuum of ionic versus covalent? And the way you tell is by the differences. Is by their differences in their electronegativity. So what they've done on this page is kind of dumb. Do you have to know this? No. But I just wrote it in. When determining electronegativity, what's nonpolar? Well, less than 0.5 difference. All right? A polar covalence in the middle, an ionic is greater. You don't have to know that. You don't have to know that. And then down here,
what's your definition of electronegativity?
My definition?
Yeah.
Isn't it just a desire for an electron?
Yeah.
So, using your knowledge of atomic structure and Coulomb's law, why is electronegativity across? Increase. Core charge does what? Increases. But shielding is constant. If the core charge increases, the shielding is constant, that core charge can pull in electrons more as you move across. Same reason that the atomic radius shrinks as you move across. So down here, I already gave you the numbers. And like I said, this is kind of stupid, but CaCl, that would be ionic. C to O would be polar covalent. And like I said, you'll never have to do this. Because they'd have to give you the whole periodic table of the electronegativities. Do you remember that in the book? There's a periodic table with all the electronegativities. This is dumb. Oxygen and oxygen, you should know. That is a truly what? That's a truly covalent, right? That's truly covalent because the electronegativities would be the exact same. That's a diatomic element. Your diatomic elements are your truly covalent elements. Yes?
I remember trying to, like, when we were in this chapter, we would, like, look at, we would find electronegativities of different compounds, and then we would test them. We're not going to have to do that on the test.
No, you're going to have to do that. HO, polar covalent. The vast majority of compounds are polar covalent. Aluminum phosphide, polar covalent. And then sodium fluoride is going to be what? You know that's going to be ionic. All right? That's a classic ionic compound.
How do you find the electronegativities?
You would have to be given them. There's no way to find them.
No,
There's no calculation
in real life, though.
by experiment. So it's an experimental thing. There's no way to find it. It has to be a chart. So, anyways, that's that. This copied horribly, so sorry. What type of ion is formed? Wait a second. Do we have the same thing? Yeah. What type of ion is formed by metals? Cation, which is positive. Non-metals is my anion, or A negative ion, which is negative. And what type of bond is formed between a metal and a non-metal? Ionic.
This makes so much more sense now.
I know. Like, the reason it makes more sense. Do you want to know the number one reason it makes more sense? Your brain is more developed. You're laughing at me, Casey?
No, from like eight months ago?
Yeah.
Yeah.
Your brain has developed that much more. You've had amazing teaching. No, but like brain development is huge. It really is huge. And like your brain's not fully developed till what, 22? Something like that. I don't think your brain fully develops till 22. Anyways. Ionic, how would you describe an ionic bond? Bonding through transfer of electrons. Transfer of electrons. Covalent is going to be sharing is covalent, right? Sharing of electrons. Sharing is caring. Sharing is covalent. That's not what I would say. Okay. And then metallic, how would you describe that?
Metal giving to non-metal.
That's just elemental. Just
What are you doing back there, Sammy?
The sea of electrons.
Yes, the sea of electrons. All right, this is delocalized electrons, right? Moving across metals, something like that. But you have a sea of electrons in a metallic bond, and they're moving across. Remember the guy holding the balls, the Vsauce we watched? They're like moving. Anyways, how would you draw an ionic bond? I draw something positive. I would draw something negative, right? And show an electron moving to the negative, something like that. How would you draw a covalent bond? I would draw something like this, sharing an electron. In a metallic bond, I'm going to have something like this, and then my electrons are kind of moving through all around. So my electrons are flowing all around for a metallic bond. How does the delocalized area contribute to the properties demonstrated by metals? Well, if the electrons are delocalized, I have a flow of electrons, so therefore it is conductor. So flow of electrons equals conductive. Oh boy. Conductive. And what about malleability and ductileness?
Yes.
Ductility. Why does this prove that they're malleable? They're malleable because what?
there's,
Why?
There's no actual bond.
It's
for
like
electrons.
They're malleable because the nuclei, all right, can move without bonds breaking. So the nuclei can move. That remember did I show you no, that's freshman. There's a movie where they're making like bells and they hit the bell and it shows how it kind of moves. Do you remember that? The nuclei don't break. If the nuclei break, if the bonds break, it's brittle. It's brittle. So that's just why it's malleable. Flip the page.
Ductility.
Ductility is the same thing as malleability. Ductility just means you can draw it into a string. So malleability is bend, ductile is into a wire. Same thing. Yeah, you got it. Then we have these things.
Oh.
Do you guys remember bond length?
Absolutely.
Yeah.
All right? So label the following on the graph.
Yes, but I never understood it.
All right? You'll understand it now, hopefully. Maybe not. Where two atoms are too close, too far, or at an optimal distance. Do you guys remember where the optimal distance is? Where?
The part on the line.
The dippy.
Yeah, part on the dippy. Yes.
The optimal distance is where the attractive and repulsive forces are kind of balanced. All right? And then this distance right here gives me my what? What does this distance give me? My bond length. And then this energy is going to give me my bond energy. So the bond length is here. Over here, they're going to be what? Too far. So these two are too far. There's not enough attraction. Here, it's the perfect amount of attraction and repulsion. It's kind of give and take. And then up here, they're way too close. They want to start repelling. Then when I start pushing back away, that's too close. This is all about your bond lengths. So over here, label the following locations on the graph. Try these. Atoms repel each other. Atoms not attracted. Bond length. I think I just gave you the answers on accident, but that's okay.
Are these graphs for any molecule?
Yeah, this is how you get the bond length of any two things bonding together. Yeah, I literally just gave you the answers, right? I'm going to repel up here. I have bond length down here. It's the first time I've done this, so I'm just kind of doing it out of my head. And then I have no attraction up here. No attraction. Okay, bond length, and bond strength. How did I teach you this? The shorter the length. Yes!
Let's go.
You got it. So bond length single is going to be my longest length, which is going to be my weakest strength. Middle. Mid. I'm so cool. All right? Shortest, strongest. Mid. The shorter the length, the stronger the strength.
I like that. That should go on a shirt.
It should, but after break we need to like get those ordered.
Which ones are we doing?
You guys need to vote.
The
Like,
ones
four
that are
people.
shorter.
We'll vote.
Oh, I-
Oh, did you put a thing on there? Okay. All right, here we go.
Everybody vote. I'm looking at
The graph at the right shows the potential energy and distance between imaginary molecules A, B, A2, B2, and C2. Which molecule has atoms that are closest to each other? What would you say? A2.
two.
Which molecule has the greatest potential
Wait.
energy?
Wait,
What?
why is it A2?
Why?
It's the
Because
closest.
my distance is the lowest.
Oh, sure.
Which molecule has the greatest potential energy in its bond?
C.
This is just reading the graph. C2.
What?
Why?
Greatest potential energy?
Remember, my energy, it's really negative potential energy. So I've got positive and negative, so I've got negative 100, negative 200, negative 300, negative 400, because we're talking about attraction and repulsion. So the farther, this would be like my axis, right? So the farther above or below is going to be the greatest energy. Now, which molecule requires the most energy in order to break the bond? Don't overthink this. It's also C2. If C2 has the greatest potential energy in its bond, it's going to require the most energy to break it. So don't overthink that. Don't overthink that. One of these molecules has a single bond, one double, one triple. Which one most likely has the double bond? Yeah, B2. B2. This next part, cross this out. Okay?
Blood.
This is talking about atomic core. I don't even know what that is. There is no such thing as atomic core. There's core charge, there's atomic radius. I even put it in my AP Chem Facebook group. They're like, I don't even know what that is. So whoever made this, I'm not sure what they were thinking. Maybe they were British. I don't know.
People are tripping.
I don't know why I said British, but it feels like a British thing. Okay. I don't know why I said that. Draw a particle diagram for the ionic solid LiF.
We're taking notes.
So I'm going to have big, small, big, small, small, big, small, big, big, small, big, something like that. What's this
Small,
called?
big.
Small.
Wait, what's after the big one?
What is this called?
Small.
Okay.
What did I just make?
Lithium small.
A crystal lattice. Which ones are the big ones? Is it Li or F?
Oh.
I've got F minus, minus, F minus, F minus, F minus. Here's my Na plus. You guys remember playing with this?
Oh,
The block, right?
that was
The green and blue balls, the magnets. I passed that around.
Does the Na have the extra shell?
Wait, isn't it?
Hold on, is this backwards?
What?
Yeah.
Lithium.
It's supposed to be.
Oh, it's the LiF.
Isn't lithium?
Oh, yeah.
Lithium should be. Wait.
Lithium
Yeah.
and fluorine.
Lithium
Fluorine
big.
is
Yeah, lithium.
smaller.
Yeah.
I would do that wrong.
Yeah.
Is
That's
it
what I was thinking.
I
I
just
think it
saw
goes
it,
like.
therefore to become larger? Yeah. Anions?
Lithium.
They have the same.
That was my
Fluorine
the
is smaller.
You know.
They have
Fluorine's
the same-
smaller.
Yeah.
So look
They
for
have the same
negativity.
shells, but fluorine has 6 more protons pulling in the radius to be smaller.
Right.
Yeah.
Yeah.
Lithium is smaller. We drew it backwards.
Electrons don't really.
No, wait.
No.
You drew it the right way.
Lithium's
Yeah,
bigger.
because anions should be-
Lithium is, as I go across the table,
Uh-huh.
what happens to atomic radius? It gets smaller.
Right.
Because I have,
So F
fluorine
is
has
smaller.
many, many more
Uh-huh.
protons pulling those electrons in,
So F is
Yeah.
smaller.
right? So F is smaller.
Yeah.
So it is backwards.
Yeah.
F is smaller. So I drew this backwards. That's unfortunate. Big, small, big, small, small, big, small, big, big, small, big, small. So,
That's the same size.
You know
yeah, what's big?
Alan?
Lithium.
Please.
Li plus. Li plus. I also drew the wrong letters too. Li plus. Li plus.
You have a hard time telling which one was the big one there.
Wait a second.
Oh.
No,
I'm losing it. This is right.
Become larger.
I promise you. this
Li is
right.
bigger, it is a fact.
Someone Google it. I'm gonna cry.
Make
The
that
answer
look
says
good.
fluorine is bigger. I don't know why.
Oh my god.
Hold on.
Yeah,
Let's just make sure here.
You know what? I get to leave in like 5 minutes. It's okay.
Well, we're gonna get this right before you leave.
Li has a greater atomic radius when compared to F. Boom, mic drop.
Thank you. Thank God.
Yep.
It's
Is
just
there
that
any
easy.
sound?
It's just that easy.
Okay, so you're saying.
But the thing is,
There's no thing.
There's no thing.
Anions have a
Mark
larger
just looked it up.
ionic radius.
I think we're thinking about when they're
you
ionic.
have, so we're thinking about this when they're atoms, right? We have to think about this when they're ions. When they're ions, what does lithium do with one electron? Loses it, which is going to make lithium actually smaller.
It says that in the dial tone up.
Okay, but is it gonna
Yeah.
make it balanced?
Yes, it is, because you're losing a whole shell.
What does it say?
So if you're going to draw this right, I was right.
It's in here.
Big, small, big, small, small, big, small, big, big, small, big, small.
It's like
My big thing has to be fluorine. I was right. You guys stop confusing me.
Used to wait.
No.
no, because
Fluorine is gaining an electron, right?
Right.
If fluorine gains an electron, what does that do with all the other electrons? What do they want to do to each other?
It becomes neon. And
They want to
then
repel,
it becomes helium.
right?
Diagram.
So you
F has a
basically
smaller
have
for
neon and helium. That's a huge difference.
F has a smaller radius.
The atom does, but not the ion. We're talking about ions.
it's in the.
We're talking about the ions. So think about this in terms of ions.
So F is the one gaining.
Correct.
Okay.
Yes.
Good call.
So I was right the first time. Then you guys confused me.
You still
So
wrote
F
NA.
is the bigger one.
Yes.
And lithium's the smaller.
I still did right. This is the right one. Oh, shoot. Yeah, you guys get it. All right, it's not that.
Wait.
Wait,
F
can you
is
write it
bigger,
just all one more
Li is
time?
smaller.
Yeah, could you
I-
do it
We
like
should have just
one
done positive, negative, negative, positive, negative, positive. You guys get it. Yes.
Small.
Okay, so considering your first diagram that was messed up though.
That was right,
That was
actually,
right.
except for NA instead of F.
Right. So if it was
Instead
NA,
of
then
LI.
wouldn't they both have the same radii?
No, because if it was NA,
Yeah.
well, yeah,
Okay.
but
Cool.
it's not. Thank you. Briefly explain why particles are arranged the way they are in the structure. Why? How do they want to arrange?
Oh.
What do they want to minimize?
Space.
Particles want to minimize
Lines.
repulsive forces. And what do they want to maximize? They want to maximize attractive forces. That's it. They want to minimize repulsive forces and maximize attractive forces. Are they announcing for the band to leave?
Yeah, some.
Okay. I heard that there were parents
You're staying here.
literally bringing in luggage of people who forgot it this morning.
Yeah. I saw.
Also, are you going to be wearing the same clothes for like 36 hours?
no.
No.
When are you going to change?
I put clothes in my carry-on.
That's smart.
Wait, are
You
you
guys
flying
fly?
now?
No, they're driving.
No.
But they'll have like a backpack on the bus and then like,
I mean, I guess some people, if they did it, then, yeah.
It's a very different answer than my freshman.
Were they
Yeah.
freshmen?
Well, you're gonna be wearing the same clothes for 36 hours? They're like, yeah.
Oh, we have to study
I
hall.
put a change
Yeah.
of clothes in my case.
That's what I would do.
Freshmen.
Next page.
Horrible.
Interstitial.
I wish.
When you hear the word interstitial, do you guys remember? Well, first of all,
It's like big and
can anybody know an example?
I got this question wrong.
Interstitial alloy would be
Notes.
steel.
Again.
This would be steel.
Oh, I thought
Alright.
steel's interstitial.
This is where carbon, right? Carbon will be the smaller, and iron would be the larger. So this is gonna look something like this. Here's my big. So it looks like this. Here's an interstitial alloy. I've got all the bigs, right? And the smalls are kind of in between. So I have two different sizes in an interstitial alloy. On a substitutional alloy, I can substitute. So this is your brass and bronze. So brass and bronze, these are your alloys. So that looks like here's a brass, one size, here's a bronze. They're all the same size. They're all the same size for substitutional because you can substitute the sizes. So interstitial, different sizes. Substitutional, same size.
It doesn't matter the order
The order,
for substitution.
the order is not actually, it's an alloy, so it's not going to be perfect. It could be some mix. This is probably a multiple choice question. Probably a multiple choice question. What would it be?
When are we
No.
taking the test the third time?
Next week sometime? Well, not during break, but the week after probably.
Next week.
Okay.
First thing Monday after break now.
Oh, that's what I was thinking, so it wasn't.
I'm not going to do that.
So I was like, we're gonna bring it.
All right, we're not going to do all of these parts. Total electrons, I don't know why we need that. So we're going to skip that. That's kind of dumb. All I really care about is valence electrons for CO2. So carbon dioxide is CO2. How many valence electrons would be in that molecule?
16.
That was fast, but yes. 16. Now we're going to draw the formula. Guess what we're about to review on the next page? Formal charge. It's coming. All right?
Ethan.
We're going to
That was easy.
review formal charge in a second.
Just
So
kind of-
carbon,
This
boom. Oxygen, oxygen. If I just put 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, that's not going to work. So I have to have double bond, 1, 2, 3, 4, 1, 2, 3, 4. Now you can answer how many shared pairs? There's 4 shared pairs. How many lone pairs? 4 lone pairs. If you want to do total, you can, but that's not important. I don't know why you'd have to write that. NH4 plus, total valence electrons. 5 plus 4 is 9, but a positive 1 is 8. So 8. What's this going to look like? N, H, 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 H. Don't forget, there's a charge. Put a bracket around it. I have to put a bracket around it. Sulfur trioxide, total valence electrons is
24.
24. How's this going to look?
Wait, what's the formula for
Yos.
Oh, sorry. Sulfur trioxide,
SO3 minus?
SO3. Yeah, SO3.
Well, there's some, no.
So that
How am I going to make this 24 and satisfy the octet rule? If I just do single,
resin.
single, is that going to work?
No,
Why not?
because it doesn't satisfy sulfur.
Because sulfur would only have 6. Do you remember the exceptions to the octet rule?
Yes.
So what's this going to look like? Let's draw our original. I need 24, right?
You do resonance, right?
If I only put a double bond here, right? Put a double bond here, it's gonna be 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. That would work, right? But this is gonna be what? Resonance. Doesn't matter where the double bond goes. It doesn't matter where the double bond goes. So you have to show resonance if there's resonance available.
What are the exceptions to the octet? Because he said BS, but then it wasn't.
Stay
always.
with me. It's on the next page. PCl5. Valence electrons.
When you're doing the resonance, should you also draw the full lone pairs on all of them, or actually?
I
just
mean, you would.
take off a lone pair on one of them.
It. There's a couple ways you can do that. I would just leave the lone pair off of one of them,
Okay.
or you could actually draw out the 3. If you want to just draw out the 3 different ones, they accept that too. So draw out triple bond here, here, and here. That's fine. PCl5, valence electrons is 40. This one's an easy one. P, Cl, 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 Cl. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. There it is. 40. 8 times 5 is 40. Good? Next page. So here it is. What is the octet rule?
The 8 rule.
Valence electrons.
Yeah. Elements want 8 electrons. They want a full outer shell. Full outer shell. When drawing Lewis structures, what should be done with the leftover electrons when the octet rule is satisfied? Where do they go? What do they go as, first of all? They go as lone pairs. Where? On what? The central atom. They usually go as lone pairs on the middle thing. They go as lone pairs on the central atom. Draw the Lewis structure for NO2. This is a weird one. NO2 has how many total valence electrons? 17. So here's N, here's O, here's O. This is funky. I'm gonna have to have a double bond, right? So here, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 2, 4, 6, 8, 10, 12, 14, 16. How many do I need total? 17.
It's just a charge then, right?
That's how you would really draw that.
No.
Would this exist?
That's good.
What's it actually going to be? It's actually going to be NO2
Plus.
plus 1, right? In nature, it would be NO2 plus 1. You would lose that electron, right? Or no, it would be NO2 minus 1, actually. It would want to gain an electron to give N that full octet. So, is it possible to have that? Sure, before bonds, but most likely not. Yes.
Even though it's only half of a lone pair, that's still sp2. 3 bonds with.
1, 2, 3, sp2. sp2. Is there resonance here? Yeah, there technically is, right? Couldn't the double bond go on either one? Why couldn't it go on this side? It could. Why couldn't I draw the double bond on this side and just flip that lone pair over there? I could, right? So watch out for that. Do I think they're going to have you be drawing out resonance structures? No. So just be aware. Be prepared. There are elements that disobey this rule. Here it is. Give an example of an element that can have more than the octet rule. Do you guys remember? The exceptions to the octet rule are BS. Remember? BS. So, carbon to silicon always have 8.
Yes,
Phosphorus above, have you ever heard that before? I made this up myself. All right? Phosphorus Well, really, I guess phosphorus / sulfur and above can have more than 8. And then boron and below can have less. Or you could literally just think about it as period 3 is where it starts. You can have expanded octet. You do it like that too. Really, aluminum, silicon are going to have 4, but you'll know. It's not nothing you have to memorize. You'll know. Give an example of an element that requires fewer than the octet rule. I just gave all of that. So lithium, or beryllium, or boron. What is the equation for determining formal charge on a particle? There's 2 equations. Equation 1, this is the one I taught you. Formal charge equals valence electrons from the periodic table minus, parentheses, lone electrons, right? So lone electrons plus, what's up? Either one, same thing. Lone electrons plus bonding divided by 2. And I'll give you an example of this. That's how I taught you. Or it could just be total valence electrons minus the assigned. So there's 2 different ways to do that. So valence electrons minus their lone electrons on it plus the bonding divided by 2, or valence electrons in the periodic table minus how many are actually assigned. Those are the 2 ways. John?
Is this for each atom in a formula?
Each individual atom in a formula.
What is an assign?
I'm going to show you.
'Cause
I'm going to show you. So how many does it actually have? We talked about that a little bit yesterday with the Lewis dot structures. Draw the Lewis structure of carbonate. Include all valid resonance structures. Label formal charges on the structures. So let's draw carbonate down here. Oh wait, is there a spot on the next page? Ah, there is. I'll do it on this page. So CO3, we know that this is CO3 2 minus, right?
sure.
So how many valence electrons do I have total? 24 valence electrons. So I'm going to have carbon, oxygen, 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 carbon, oxygen, 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 carbon, oxygen, oxygen, oxygen. They asked me to draw all of them. And these are all 2 minus, 2 minus, 2 minus, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4. Pause while you're finishing this up for commercial break by the real Sam Smith. He has a book he wants to show you.
Oh.
I do.
Yeah, don't you have a book?
Did you buy that?
Wait, which one's the most sensitive?
So, Sam showed me this book this morning. And what do you want to tell people about this book, Sam?
It's really good.
It's really good.
Wow.
That's not what he told me.
What?
He told me that it was really helpful, and he got this book for physics.
Chemistry.
Oh, no, you said, didn't you get the same book for physics?
No.
What?
I said I got it in the beginning of the year, like
I
before.
think you said it helped you get a 4 on something. Or was
No,
that
I was talking about the videos. I was like,
Oh, got it.
That's-
Anyways, this book's pretty good. He showed me. It's another way, just another study tool. And he said it's could be yours for the low price of $20. So, another option.
what?
You can see it's
Secrets of
literally
Long Life.
exactly what we're talking about here. And it's colorful. So another study option. Fast Track Chemistry by the Princeton Review. It's a review for AP, honors, and other advanced study chemistry. $20 could be yours. Thanks,
So
Sam.
how many
Give Sam a
pages?
round of applause
I'll
for
give you
sharing that.
5 for what's
And I also posted the book I recommend too. So,
200.
I thought they were announcing it.
Jeez.
I think it's like a
All right, so let's do this molecule. All right, Let's label this oxygen 1, oxygen 2, oxygen 3.
Yeah.
All right? Let's calculate the formal charge for carbon first. So, for carbon, if you go back to your equation, it is valence electrons. How many valence electrons does carbon have? 4. So it would be 4 minus the lone. Does carbon have any lone pairs?
No.
0. Plus bonding electrons. How many electrons does carbon have bonded to it? 2, 4, 6, 8, right? 8 divided by 2. So 4 minus 4 is 0. Or you could do valence electrons minus assigned. How many valence electrons does carbon have? 4. How many are actually assigned to it, though? There's only actually 4 assigned to it, right? Because it's really only sharing 1 electron from each of those. So I've got 1, 2, 3, 4. 4 minus 4 is also 0. So that's the assigned. Actually, that's a little bit easier. However you want to do it. Oxygen 1. Let's do it the other way. How many valence electrons does oxygen have? 6. Minus assigned. How many electrons are assigned to it? 2, 4, 6, plus 1 is 7, so that's negative 1. Or we can do it this way. We get the same answer. Oxygen 2. How many valence electrons does oxygen have? 6. How many are assigned to it? 1, 2, 3, 4, 5, 6. It's sharing 1 here, right? Minus 7 is negative 1. Oxygen 3. How many valence electrons? 6 minus, how many are assigned? 1, 2, 3, 4, 5, 6. 6 minus 6 is? That's formal charge. Are any one of these any better than the other?
Yeah.
No. These would all be the same. You're just moving the double bond, hence resonance. Right? But sulfate does not work like that. Okay? So sulfate, SO4 2 minus. How many total valence electrons?
26.
32.
32. 32 valence electrons. Let's draw it this way first. 1, 2, 3, just like that. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Are you sure there's an announcement coming? I don't want you to be late.
It's like
I
a
haven't
1 that we have
seen
to be
it.
there.
I don't know.
Mr. French sent an email out earlier. He said, please dismiss these at 12:45. So,
A few more minutes on.
would this work?
House of God.
Would this satisfy the octet rule?
Yeah.
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 What would the formal charge be on sulfur?
2.
It would be, how many valence electrons does it have? 6. How many are assigned?
4.
2. So that would be 2. Oxygens are all going to be what?
0. Oh, negative 1.
Negative 1.
They're all going to be negative 1, right? So I've got 2 for sulfur. Oxygens are all negative 1. Could I draw this a different way?
Yeah.
Yes.
No.
Could I draw like this? Could I use a double bond on one of these? Could I draw it like that?
Why would you?
Why would you? That's a good question.
Because we want our formal charges on the individual atoms to all be 0 if possible. Right?
Wait, you want your formal charge on what?
You want all the individual formal charges to be 0 if possible. So, formal charge here is still minus 1, minus 1, minus 1. What's this one going to be?
0. For oxygen?
For this one. Valence electrons it has is 6. How many are assigned? 1, 2, 3, 4, 5, 6. That is 0. 6 minus 6 is 0. Agreed?
Oh, I'm tripping.
What's this sulfur now?
-1.
Valence electron sulfur has
6.
6. How many are assigned?
5.
5. So that is +1. So I've got some positive ones, I've got some negative ones, I've got some zeros. Could I draw this another way?
Oh my god.
No.
You could.
No, you can't.
No, you can stop.
Double bond, double bond.
You cannot.
I got it.
Could I draw it like that? I could. 1, 2, 3, 4. 1, 2, 3, 4. This is a really good example of formal charge. 1, 2, 3, 4. 1, 2, 3, 4. Formal charge in this oxygen. 6 minus 1, 2, 4, 6, 7 is
-1.
-1. This one's also going to be -1. What's this sulfur going to be?
0.
0. What's this oxygen going to be?
0.
0. What's this oxygen going to be?
0.
So I have 0, 0, 0, -1, -1. It's this one. Has the most zeros.
Wait,
That's
can you,
formal
Can you
charge.
just do another double bond? No.
No, it won't work.
No.
No, it won't. 'Cause then
Will not
sulfur
work.
is-
Right.
Screwed up on the one.
Will not work. That's formal charge.
So if you're asked to draw as a 4-2 minus, that's the only right one.
Yeah. That's the correct one. It's the correct one.
Really?
I don't think you're going to be asked to do that, though. I really don't. That takes way too much time. No. What information? Sorry. We'll take a 5-minute break at 12:45. What information is given? Bond order. This is something you should have learned in CP Chem. I don't know if you did. This is really simple. Okay? Really simple. This is just the number of bonds between atoms. This is so easy. All right? The equation BO equals number of bonds, right? Divided by number of domains. That's it. How many bonds are there in how many domains? The domains are just your bonding sites, right? So how many bonding sites, how many domains? And then all you have to know is as the bond order increases, the bond strength is also going to increase. Think about that, right? The more bonds I have per domain, I'm starting double and triple bonds, right? The shorter the strength, the stronger the strength. This is just another way to talk about double and triple bonds. The shorter the length, the stronger the strength. I need a 5-minute break
The
too.
longer the length, the stronger the strength.
No. So here we go. For acetaminophen, which is the active ingredient in Tylenol. Tylenol.
They're the same
Not Advil.
thing.
Is it the same thing?
No, because one of them's an NSAID and the other one is not.
I don't think so.
Oh, okay.
Anyways,
Aspirin's an NSAID, acetaminophen is not.
here's the molecule. This is identify the hybridization of the carbon involved in the double bond on the left side of the structure. So, first of all, this is an organic molecule. Which carbon am I talking about?
The one connected to the O.
I gotta be talking about this carbon. Right, this is a stick structure. So, how many things do I have coming off that? 1, 2, 3 things coming off of that.
SP2.
SP2, bada boom, bada bing. What is the bond order for the nitrogen atom? Nitrogen has how many domains?
3.
1, 2, 3. Agreed? Divided by
Wait,
how
wait.
many? What?
Where are you seeing domains?
Nitrogen has 3 possible places it can bond.
Right.
1, 2, 3. How many things are connected? 1, 2, 3. 3 divided by 3 is 1.
Wait.
That's bond order. That's it. So all you're looking at is, for domains, you're seeing how many things are connected to it and how many spots. And then for your actual, it's bonds, right? So how many bonds? It has 1, 2, 3 bonds over 1, 2, 3 domains. I'm just counting.
So if there's a double bond, it would be 4 over 3.
Yeah.
Yes. John,
Do the lone pairs not count as domains?
the lone pairs?
Yeah.
There would be no lone pairs on that.
But would they count if it had some?
it would not matter because
There's 10
no,
seconds.
I don't.
till it's
Because it's all about bonds. Bond order is about actual bonds. What's the Vesper shape of this nitrogen molecule? What's the shape?
Yes.
Trigonal.
Trigonal what?
This is Baron's bus.
Trigonal pyramidal.
I think Alan needs to go.
Alan, that's not.
We're finishing this page.
Oh, nice.
Actually, that's good.
You didn't show us-
Band people leave. We'll take a 5-minute break.
What am I doing?
Band people have a great break.
Yeah.
I will finish this. Here we go. Using Vesper. Why does a molecule have this shape? Why is it trigonal pyramidal? What do the electrons at the top here do?
Push down.
Yeah, we know that electrons repel, right?
Oh yeah.
The electrons, parentheses, the lone pair, right? Pushes others down. You go from this to this. A very accurate description. You're going from this to this.
It's a very calm class.
Is it that much different without? Yeah, it is. Just a different dynamic.
Wait, did John just say this?
That's my stuff.
I was wondering if John. I was wondering if he did. I'm like, I could see him doing that. But all right, let's finish this up.
As soon as John left, Sam was like,
What is the bond angle of C double bonded O? So we have to go back here.
109. I was just drawing
That's one of the ones, but not this one.
Hold on. Oh, it's the one on the
We're
far
talking
right.
about.
109.5.
We're talking about. We're here now.
Is that 120?
All right.
1, 2, 3.
There's 3. 120.
Let's go.
120 degrees.
Explain why you.
Explain. We know because we know they want to stay apart from each other.
I'm putting Vino.
We know. Yes. Single bond. How many sigma bonds would that have?
1, 1, 1. They're all 1.
A double bond would have how many sigma bonds?
1.
A triple bond would have 1. How many pi bonds for a single?
0.
How many pi bonds for a double?
1.
How many pi bonds for a triple?
2.
Why do you do words?
I don't know.
Yeah, 1.
I don't know why I did that. My brain just decided to do that.
Really good.
We need to finish this.
You know what? Oh, there's no back.
Do you remember how hard this was when we learned that originally?
It's still pretty difficult.
Single bond, sigma bond, double bond, sigma pi, triple bond, sigma pi pi.
Oh, love it.
Okay.
Maybe.
Circle 1 sigma and 1 pi bond.
Can you just like circle one of the double bonds and just say that's sigma?
There's a pi, but there's also a sigma, right? As long as you don't circle a single bond and label that as a pi, you're good. How many total sigma bonds? Ooh. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Oh, but then you also have to consider there's hydrogens coming off of here too, right? There'd be one here. There would be one, let's see, here. There'd be one here. 15, 16, 17. 17.
Wait, there's 17.
Yeah, because it's not showing it, but there's actually hydrogens coming off of there.
We'll talk later.
We're just counting. We're counting single bonds. That's it.
I'm counting 18.
I counted
Is
17.
the N to the H also a single one?
That's a single.
Yeah.
Wait, can you stop
I got
the
18.
bonds?
Can I what?
Can you like point to the bottom?
This one doesn't have.
I'm going to go right to left this
This one
time.
doesn't count that. So
1, 2,
you see I crossed it out.
4, 5, 6. Oh, shoot. I got 17.
Let's just.
The double bonds just 1, 2?
Double bonds are just 1.
Yeah.
Because we're just doing sigma bonds.
So is it just the number of like lines? Literally?
Not all the lines, because this is only, a double bond's only 1. But there's technically a hydrogen here, there's a hydrogen here, and a hydrogen here. So it'd be 17. How many pi bonds? 1, 2, 3, 4, 5, 6.
Yeah.
Done. Unit 2. We've now technically gone over 3 of the 9. I'm not going to go over Unit 9 again. We just did that. Your homework over.
Yeah, that's 17.
No homework.
Work over what?
So
No.